Hello again, everybody. Welcome back to a new screencast lecture. Today is called Phase Change Chart or Phase Change Graph. This is kind of an accumulation of everything that we've learned up to this point. So this is a really important lecture, so make sure you follow along carefully. When thermal energy is absorbed or released, matter can change from one state to another. And there are several different types of phase changes, like, for example, melting, freezing, vaporization, condensation, sublimation, deposition. You should know what all of those mean. Here's a clip. This will show the heating curve of water. They're going to start with a block of ice, and they have an electronic thermometer, which will record to the computer. And this is really a neat clip. I wish I had the ability to do this. Here you can see, and I'm going to pause and start and stop this and discuss this as we talk about this, but here you see a block of ice. This is the probe, and it's recording the temperature here. So here you see the temperature is increasing, and as we go from left to right, this is time that's going by, and it's being heated up. You can't see it, but underneath here, there's a hot plate, so it's heating it up. We're increasing the thermal energy as we go this direction, and then this is going to be the temperature on this axis. Okay, the temperature is going up pretty steadily. Now, this is the really interesting part. As we get close to 0 degrees Celsius, and you should know that 0 degrees Celsius, that's going to be the melting point of water, watch what happens. So here it was going up pretty steadily. As we get to 0 degrees, look what happens. Look how it kind of flattens out. Oops, I like to call that plateauing. So here you see that it goes up steadily, and then here at its melting point at roughly 0 degrees, it plateaus. It stays at the same temperature. However, we're still increasing thermal energy. So it's still being heated up. However, the temperature's not going up. And that's really pretty interesting. Now, this next clip combines this, and now they're going to be starting at the point we were just at, so at the melting point of water. So we're at 0 degrees, and notice we're still having that plateau. So it's still increasing thermal energy, but the temperature's not rising. That's the really cool part. Okay, now let's take a look at the jar. Now there's ice in this jar, and there's liquid water in the jar. So if you take a look here, we're going to go backwards here. Here it's primarily ice cubes. However, you can still see that there is some liquid water in there. All right, and so we have both liquid water and solid water at this point. Now at this point, we get a little bit of a increase in temperature. However, that's not meaning a whole lot. It's still relatively flat. It's still relatively hitting that plateau right here. Still kind of creeping up, You see there's still liquid water. There's still solid water. That's kind of the key. There's still solid water. There's still ice there. Now, if we watch what's in the beaker, almost all the solid water is gone. And once that solid water is gone, oops, what in the world did I do? Once that solid water is gone, that's where it gets really interesting. So here we were. So here's the ice cube, the solid water. The solid water is now gone. Okay, now watch what happens to the temperature. So we stayed fairly flat, pretty close to 0 degrees here. Plateau, and then when it's all just liquid water, watch what's going to happen. It's going to skyrocket like this. Okay, see, now it's going up steadily. Yeah, I think that's really interesting. I remember when I was young, the first time I ever saw that, it really kind of confused me because I was thinking, why isn't the temperature increasing? The ice is melting. Well, that's key. It's because the thermal energy is being used to change the phase. The thermal energy is not being used to increase the temperature. The thermal energy is being used to change its phase from solid to liquid. So if you remember, solid water is at a lower energy level than liquid water. So here's solid water, and then it's changing from solid to liquid. We're increasing thermal energy, but we're not increasing temperature The thermal energy is being used to change phase, not to change temperature. And then here, at this point, it's all now liquid water. So now that thermal energy is being used to increase temperature. Pretty cool. Oh, now it's starting to boil. Now this video kind of cuts off really close to this part, so there's not a whole lot more to see here. However, notice that when we get to the boiling point, again, now we have liquid and gas in the jar, so we should expect to see another plateau. And sure enough, I'll go frame by frame here, and you'll see that that plateau is happening. So we have a plateau here when we have a change from solid to liquid. It goes straight up when we're at all liquid, so the temperature increases. When we get to that phase change again, the temperature is not going to be increasing. The temperature is going to be staying the same, and the thermal energy is still increasing because we're going from liquid to a gas, and gas is at a much higher thermal energy level than liquid water, even though it's the same temperature. Pretty cool. All right. Now here's a chart, and this is kind of like the same chart that we just saw. Here we saw the block of ice. As it warms up, it's all still ice. It starts to warm up, Now when we get to here, this is that plateau where we're going from solid to liquid. The temperature is not increasing. Then after all of the solid ice melts, it's now liquid water. So now the temperature shoots up. We start seeing bubbles. We start seeing steam. The temperature plateaus again. And we get the phase change from liquid water to gas water. Water in gas form, like water vapor, and steam in this case. And so we're not having the temperature increase, but we are having the thermal energy increase. Now what's interesting about this is notice that this line compared to this line is going to be much, much longer. In fact, it's going to go way off the screen before it starts turning all into gas. And that's because it takes way more thermal energy to go from a liquid to a gas than it does to go from solid to liquid. Now, just follow along here. Don't try to write this down yet. I will let you know when we get out the accompanying guided notes paper that is attached to this assignment on Google Classroom. If you're just watching this only on YouTube, I'll try to figure out a way to have the chart, but you'll be able to see it. I don't know if I can attach a PDF. I'm not really sure. Don't know how to do that, but maybe I can find out. What I would do is print out 2 copies of that chart that we're about to go through right now. Okay, here's a blank part of the chart. Now, remember, this is our graph. What is down on the x-axis? This is going to be the time sitting on the hot plate or sitting over the burner. A better way to say this is the amount of thermal energy. So it's the amount of thermal energy as you go from left to right, the thermal energy is going to increase. On the y-axis, this is going to be what? Well, it's temperature. And as we go from left to right, what's happening to thermal energy? It is increasing. As we go from bottom to top with temperature, what is happening to temperature? It is also increasing. So as we go left to right, thermal energy increases. As we go bottom to top, temperature increases. Now, we always need a title. What would be a good descriptive title? A good title for this is going to be phase change of a crystalline solid or a crystalline substance. The phase changes for an amorphous solid would not look like this. So, for example, this would work for an ice cube, which is a crystalline solid, but it would not work for a block of wax. That is an amorphous solid. So here's our title, phase change of a crystalline solid. And this part of the graph, this is when we're going from here to here. Notice it's a pretty steady increase. What is the phase at this point? It should be in the solid form. And then what does the line do? This line here, what will this line do as the solid starts to melt to a liquid? It should plateau. It should flatten or plateau at this point. So we're going to have solid and liquid in the beaker. The temperature, you notice, is not rising. What is the added energy being used to do? So we are increasing thermal energy. It's still sitting on the hot plate. It's still gaining more of that thermal energy from the hot plate. What is that energy being used to do? It's not being used to raise the temperature. Therefore, it is being used to change its phase. Because remember, the liquid is at a higher energy level than the solid. So even though it's at the same temperature, that plateau line, the thermal energy here, this is going to be solid and liquid, versus here, they're both the same temperature. This liquid is going to be at a higher thermal energy level than the solid at this point. What does the line do when it all becomes liquid? So it's solid, liquid. Here it is solid. Here it's solid and liquid. When it all becomes liquid, now that temperature line is going to increase. The substance has completed the phase change from solid to liquid. What does the line do as the liquid starts to vaporize? So here we go. This is all liquid. Temperature goes up, 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 up. What does the line do as the liquid starts to vaporize? So as we start seeing steam and bubbles, we should expect that temperature line to plateau. And because the energy is not being used to increase temperature, it is being used to change from a liquid to a gas. It takes thermal energy, it takes a lot of thermal energy to go from a liquid to a gas. Remember, gas is at a higher energy level than liquid. What does the line do when all of the substances have vaporized? So we go here from liquid, and then here it's going to be all gas. We're going to have liquid and gas here, liquid and gas, a little bit more liquid than gas, and more gas than liquid, and then finally here at this point it's going to be all gas. What should we expect the line to do now that the phase change is complete? Well, of course, we should expect that line to start shooting up. The temperature should increase. Now, let's go through and name all of the types of phase changes shown as you increase energy in this case. So we're here from a solid to a solid and a liquid. What is this phase change called, going from a solid to a liquid? Of course, that's melting. Now we have a liquid, and we're going to change that from a liquid to a gas. That is called vaporization. Now let's go ahead and decrease the amount of thermal energy. So now in this case, instead of going up the chart, we're not going down the chart. So we're going from right to left. So we're not going back in time. That's why I don't like having this be time. We're going back this direction. We're taking away thermal energy. So let's take away thermal energy from a gas, 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 gas. Now gas, liquid, gas, liquid, gas, liquid, liquid, gas, liquid, gas, liquid, liquid, all liquid. What is that called here? And then if we go down from liquid, 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 liquid to solid, liquid, 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 solid, solid, liquid, solid, liquid, solid, 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 liquid, solid, solid, and then we go back down here all solid. So here's the first one. So going from liquid to solid, that is called freezing. Ta-da! Notice I have the plus here. That means I'm adding thermal energy. That's melting. If I'm taking away thermal energy, that's going to be freezing. Now as we go from gas to liquid, that is going to be called condensation, and we are taking away thermal energy, condensation. What causes any phase change to occur? Any phase change requires either the addition or the removal of thermal energy. Now, get out your worksheet that looks like this, and what I want you to do is to copy this next slide onto your guided notes worksheet. I know there's a lot there, but this is a great chart and it's really helpful. So go ahead and pause here and copy this down. Moving on, now let's talk about the particles, the motion of particles and how they relate to the phases that they are in. Get out your second copy of the chart. I will tell you which slide to copy, so don't start trying to copy everything now. I'll let you know just like I did with the first portion. We're going to draw what the particles would look like for a solid, and we're going to draw that in the location of where the particles will be all solid. They should be here, no, here, no, here, no, kind of here, but here would be the right location. How would you describe the motion of the particles in a solid? So here we're going to draw the particles right here, and we're going to describe the motion of the particles in a solid. I would say that the particles in a solid vibrate in place, and the key to that is that they do not change position, and they're going to be moving slower than the particles in a liquid. Now we're going to draw what the particles would look like in a liquid, and their location would be here because this is where all the particles would be a liquid. So we're going to draw these. We still have the same number of particles, 6 particles. Notice they are no longer in that rigid crystalline shape. So how do we describe the motion of the particles in the liquid? Well, the particles in a liquid are going to spread out further than the particles in a solid, and most importantly, they can now change position. So this one can go here, and this one can go there, and this one can go there. They also are moving faster than the particles in a solid. We're going to draw arrows to show the movement that the particles would look like for a liquid. So we would draw something that looks like this. And we should have some sort of container potentially, and the particles in the liquid are going to stay in that container. Notice that the arrows are not very long. That's to represent that the particles are spreading out, they're changing position, but they're not doing it really, really fast. They're not going really, really far. Compared to the gas, they're not moving nearly as fast, they're not moving away from each other nearly as far. Now we're going to look at the movement of particles in a gas. So here's particles in a gas. They go up here, and this is really not drawn to scale because, I mean, these are pretty close together. These are pretty close together. These don't look that far apart, and they're kind of farther apart. But really, these particles should be like not even on the screen. They should be spread out quite a bit. Let's go ahead and look at the movement here. The first thing is the particles in a gas are going to spread out further than a liquid, and they will spread out as far as they can. They will, especially if the container is open, they're going to try to escape the container. They move faster than the particles in a liquid. And we can show the motion by drawing arrows. We're going to draw arrows to show the movement of the particles for the gas. Here are the arrows for movement in a liquid, and these are arrows that you would show and draw for particles in a gas. Notice that the arrows are much, much longer than the arrows for a liquid. This shows that they're moving much faster, and it shows that they're spread much farther apart than the particles in the liquid. Now notice I have the star here. This is what I want you to draw. Please draw this out, draw the particles, and draw the arrows of motion. All right, guys, well, that's it. Really, that's really good, important stuff. One of the keys to remember, guys, is just really remember that, again, solid, the energy level's down here. Liquid, it's a little bit higher. And then gas, it's way up here. So the energy level of gas is way higher than a liquid. And we're going to get that chart that kind of looks like this, where it goes up, up, up as a solid. It's going to plateau, going from solid to liquid. It's going to shoot up as long as everything's a liquid. Then you're going to have that long plateau going from a liquid to a gas, and then it's going to shoot up really, really quick as all of the particles are in a gas. All right, guys, have a great evening. See ya.